All right, excellent. All right, so again, welcome, Matei. Today, Matei will talk about faster and cheaper training of large language models. I think this area is super interesting to everyone. And without further ado, take it away, Matei.
All right, thanks a lot, Alexi. So let me just share this. Cool, you can see these slides, right?
Yep, very good.
Oh, yeah. And yeah, since you mentioned Apache Spark, I do want to very quickly say that version 3.2 just got released today. If you use that, check it out. But for the rest of the talk, I'm actually going to talk about research that my group is doing at Stanford with a whole bunch of collaborators on faster and cheaper large-scale model training. So that's been a really interesting area to work in, and I'll talk about different ways to tackle it and what could work best in the future, at least what we think about it. So I think everyone has seen how machine learning models are growing larger and larger every year, and for natural language in particular, that's where they've been going at the fastest rate, but this is also true in other domains. So this plot here shows the just language models, and you can see they're growing exponentially. It's a log scale, and they've actually grown in size by basically like more than 1,000x since 2018. And the interesting thing is this is actually faster than another exponential trend, which is how quickly we're making hardware faster. So the hardware people are working really hard, getting lots of revenue from selling all these GPUs and stuff. And even then they can't catch up with, with the way these models are going. So obviously there's a big problem to make, state-of-the-art ML broadly accessible. How do you make it cheaper to train these things? So I'm going to talk about two approaches and talk about some research we did on each one. The first one is just take today's models and try to design computer systems that are going to train them faster. Makes a lot of sense. There are a lot of people working on this. In my group, we did a bunch of interesting, early work in a few directions. And one that I'll talk about is opening up new ways to parallelize ML training that actually improve device utilization and ultimately improve the throughput you can get. So we have this idea of pipeline parallelism, and some of the things we developed are now part of open source software like Megatron-LM from NVIDIA that can be used to train large models, and they're also being adopted in others. But then there's another approach we can take, which is don't try to use today's DNN models, try to design new machine learning models and algorithms that are actually more systems friendly. And this is the one I'm really excited about, because I think the first one, even if we work really hard, there are going to be limits to how fast we can make things. And I'll talk about something specific to NLP, which is we've been exploring these retrieval-based models, and we actually produced a bunch of models like ColBERT and Baleen that are setting basically state-of-the-art results in NLP, but also run much faster than the large language models you usually hear about, like GPT-3. Okay, so let me start with that first one. So what can we do with existing models? How can we run them better? So obviously with these huge models and huge data sets, you have to parallelize training to make it go faster. And it turns out there are a lot of ways, if you're training a neural network, to parallelize it. So in the past, there are two approaches that are really common that you can hear about everywhere. And some of them are easily supported in frameworks like TensorFlow too. The first one is data parallelism. In this one, you take your model and you just put different copies of it on each machine you have, or say on each GPU. So that's a copy of the whole model. And the thing you parallelize across is just the input data. So for the batches of data you train on, you just split them, say, across 100 devices, and each device does like one 100th of the work. So that's really easy to implement. That's why systems like TensorFlow and PyTorch can easily do this by default. And it definitely gets some benefits, but it has some problems. One of the problems is like your model actually has to fit on every machine, and that itself can be a problem when you get to these huge models. So that might be a showstopper if it just doesn't fit. And the second problem is that you have to communicate to synchronize the weights or the gradient updates between the workers. And that cost is also proportional to the size of the model. And that can easily become a bottleneck as well. So this isn't usually the best way to just scale up a model. And the second thing is the second approach is model parallelism, where you take your model and you actually split up the parameters onto different machines, or split up, say, the layers. And then the nice thing about that is if you have a huge model, no worker needs to have the whole thing in memory. It can each have a little subset. So that's really good. Is only one copy of each weight. And then the other thing is it does usually result in cheaper communication. So this is what a lot of the the people who train huge models were doing, is actually model parallelism. So what's challenging about parallelizing things? Well, in both cases, the thing you have to worry about is utilization of the hardware, and this is where we spent a lot of work trying to improve this. And it turns out that actually model parallelism, the thing that people use for huge models, also has challenges with utilization. So I'll explain how that works. So to understand that, so actually it turns out model parallelism is one of the worst things you can do if you want high utilization of your hardware and therefore high throughput and low cost. And basically, to see why that is, you have to think about what each worker is doing at each point in time. So remember, we took our model and we divided its layers across workers. In this case, I'm showing 4 workers. So what are they each doing at a point in time? So in ML training, you have basically, you keep doing switching between doing forward passes and backward passes that together help you update your weights. And so in the forward pass, you take some input batch of records and their labels, and you pass it through the model from the first layer to the last. And to do that with model parallelism, that means that in the first time step, only the first worker is doing any work because it has the first few layers. So the other ones are all idle, which is shown here on the timeline. They're not doing anything. Then when it's done with that, the second worker does its layers and the rest are all idle because they've got nothing to do, and so on. So throughout the forward pass, basically there's only one worker active at a time. Makes sense because only one worker has the weights for that layer. And then the same thing happens in the backward pass. You go back and pass back some information. And again, only the last worker can do anything because it has the last weights. And then, worker 3 can do stuff, then worker 2, and then worker 1. So even though you fit your model onto lots of devices and you purchase these really expensive GPUs from NVIDIA or whatever to do it, or you rented them out in the cloud, most of your GPUs are idle, 3/4 of the time here because they're waiting on other things to finish. So it's not a very efficient way. And this is where we can actually make the cost, a whole lot cheaper than this and get a huge improvement in cost, like 4x ideally is the most we could imagine getting here. Okay, so how can you improve this? So one general approach that you can do is called pipelining. And so we looked into this starting a few years ago, and others have been looking into it as well. And I'll show first a more basic pipelining scheme and then a more advanced one that we came up with. So one of the ways to do pipelining, and this is actually a few papers proposed this, well, an example is the GPipe paper from Google, is basically looking at the previous picture. Let's actually split the batches that are passing through each worker into even smaller batches. Sort of take your mini batch and split it into micro batches. They're getting pretty small here. And the nice thing about that is, as the first worker begins processing each batch, once it finishes, say, 1/4 of it, it can pass that on to worker 2, and that one can begin computing stuff at the same time. So, and then same as it keeps completing chunks of it, it just pushes them forward through all the other workers. So compared to the previous picture, you can see there's less gray space on the picture. These workers are actually overlapping a whole bunch as they do, the forward pass, and then the same thing happens in the backward pass. And in an ideal state, you could get basically like 50% utilization by doing this. So that's not too bad. But there is a problem with this, which is the way that gradient descent works in machine learning. You have to wait before you begin the next iteration of forward and backward passes. You have to apply all the updates from the previous one to actually move your weights forward and apply the gradient you computed. And so that means you have to flush the pipeline. You have to tell everyone, hold up, wait a little bit at the end of each of these steps. And that really keeps your utilization low overall, because even though you're ramping up, keeping everyone busy for like some fraction of the time, you always have to slow down before you can start the next thing. So that's the problem with this. So one of the things that we worked on that addresses this is we actually changed the machine learning algorithm, like the gradient descent algorithm, to eliminate the need for waiting after each update. And so we designed a few ways of doing this. And one way that I'll talk about that we published this year is called double buffered wait update. So we have this system, PipeDream, that does it. And we also implemented it in other ones. And basically what this does is, if you look at the bottom here, it actually changes the gradient descent sort of formula that we're going to use. So normally in grade descent, your weight at time t+1 is weight at t minus learning rate times the gradient of weight at t. And we actually changed this from t to t-1. So actually at each time step, we're applying a gradient update from computed with an older version of the weight. So all the updates are delayed, but it's delayed in a deterministic way. You're still going to get all of them. So we're applying this sort of stale update. And the nice thing with this is it turns out if you're willing to do this, you can actually ramp up and keep the pipeline full all the time. And the way that will happen is each worker will actually have to hold basically 2 copies of its weights. It will have to hold the weight from a few time steps ago and the current weight. What will happen is, as you do this forward pass, everyone computes that, everyone computes the backward pass, and when the backward pass for that first version of the weights gets to the first worker, that's when it will begin using these updated weights. But in the meantime, it already started doing another forward pass with the original weights. And that's going to keep going until actually, I guess 8 also has to use the original weights, and that's going to keep going and give you an update based on those. So it's a little bit, maybe it's a bit tricky to see from the picture unless you think about it. You spend a lot of time to think about it, but basically after the first step here, you can always keep everyone busy at all times. And the main cost is you are getting these delayed updates, and you have to double your use of memory on each worker. So you have to keep 2 copies of the weights. But that's not too bad because, the whole point of this was we were gonna, we could split our layers onto different workers. So hopefully each layer is small enough that you can do this. So that's the approach that we did there. Just to show you a little bit of like the performance you can get with this, it actually can give you pretty big performance gains for real models like GPT-2 in this case, without affecting convergence really. So at the top here we have basically we're showing throughput with different batch sizes, and we have the blue here and the orange are simple ways of doing model parallelism, like I showed in the first picture, and then these gpipe is the more sophisticated way that still has flushes, and then this PipeDream 2BW is the one is sort of the highest throughput one that we came up with, and you can see it's quite a bit faster, right? So this is how I think this was on 8 servers with 8 GPUs. So and overall it's close to a factor of 10 faster and therefore cheaper. And at the bottom here, these are the training and validation loss. You can see we're a little bit behind on both. We take a little longer to get to the same loss, but at the end of the day, we do get to the same thing, and it's worth it given the speed up. This is showing in iterations. So that's one of the techniques that we've come up with, and there are other ways as well. A question about all this stuff is, hey, I talked about how utilizing the hardware is the really difficult part, especially if you have to spend time communicating or waiting for other things. So how close do we get? So we actually collaborated with the Megatron team at NVIDIA, and we tried, we used pipeline parallelism. We also used other tricks. We used a combination of data parallelism and splitting each tensor too across multiple devices. And we actually tried training a 1 trillion parameter model on 3,000 GPUs. And by carefully tuning this was all led by my student Deepak, who recently got his PhD and graduated. We were able to get 50% of peak efficiency on 3,000 GPUs. That might not sound like a lot, but actually in high performance computing at this scale, that's considered pretty good. It's hard to get that to, kind of balance communication and computation in a way where you're actually using like that high of a percentage of the floating point operations that these devices can do. And this is open source on NVIDIA's site. Recently, they also published some accuracy results with this type of model, not using our training system. It's actually, they were training that one earlier, but basically, it does actually get good results on language tasks. So that's pretty nice. But there is kind of a problem. Like if you think about it, right? One way to think about this is, regardless of how hard we work on the system side, we can only make things 2 times more efficient. And this type of system, even though it's, like a factor of 10 faster than previous parallelism approaches, it will still take weeks or months to train a model on lots of GPUs. So it's still really expensive. I should also mention there are many other interesting pieces of research in this area. So another project I worked on that I won't really cover here is to automate parallelization. Like in this case, Deepak manually, configured models and figured out how to tune them and how to divide things. But most people probably don't want to do that. And my student Zhihao Jia actually developed a framework called FlexFlow that's also open source and that does this automatically. He's actually giving a talk this Thursday at the Stanford ML seminar, which is streamed and recorded on YouTube if you want to check it out. So definitely encourage you to see that, because he's done really cool kind of compilers and automatic optimization work to make this type of thing accessible. Okay, but at a high level, like, okay, we've made good strides, but it's still going to be pretty expensive to train things this way. And there's also some bad news, even if you have very high budget. If you're saying, I don't mind using 3,000 GPUs or even like 10,000 GPUs, just give me the model. It's actually hard to scale beyond where we are now for other reasons as well. And this is basically because as you increase each dimension, you start to get diminishing returns. So for example, in that result, the Megatron result, we did use some amount of data parallelism. We took each batch and we split it into smaller pieces and gave them to different parts of the system. The problem is, you don't want to make the batches too large in gradient descent, because you get limited signal. Like basically, it's better to take more gradient steps with sort of a medium-sized batch than a few steps with a huge batch. So there are diminishing returns to just increasing the batch size. And if we keep the batch size small, the problem with parallelizing across more nodes is that each node starts to get so little input data that it can't actually fully utilize the hardware on the GPU. So it can't, like for example, you're trying to multiply matrices, and if one of your matrices is like 100 by 1, you're not going to get all the peak flops that like NVIDIA can attain for matrix multiplication. Those are attained when you get big matrices, like say 100 by 100 or something, where it can actually optimize and cache stuff across both dimensions. So that's a problem. And same thing with pipeline parallelism. If you already put each layer on a different device, it means you can't do more pipelining. You're already maximally pipelined. So it's actually hard to even to scale this kind of thing past the 3,000 GPUs we had. Okay, so that's kind of the state of this stuff. Hopefully it gives you some insight on what can happen there. So then the other thing I wanted to talk about, let me just check my time here. Okay, it's good, is a totally different approach, which is what if we design ML models differently so that they're actually more systems friendly. And this is an area I'm excited about. It's still pretty new, but a bunch of people are working on this kind of thing. So in this, we focus specifically on natural language, but you could imagine doing some of this and other stuff too. And we're excited to try it there as well. So let's think about like, hey, how does large-scale NLP work today? All the results you read about where people are doing really well on benchmarks and so on recently have been using these huge DNN models like GPT-3. And the idea there is you take this model and you train it over massive amount of text, like everything on the web or a curated subset of the web that you think actually has accurate information. And then it basically encodes knowledge in its weights somehow about all kinds of topics. And then you can ask it a very specialized question like what protects the digestive system against infection, and it can actually give you a meaningful answer based on the knowledge it learned, modeling stuff on the web. So that's nice, very, very impressive that it can do something like this. But then if you think about, hey, practically using this, there are a lot of challenges. First of all, it's really expensive to train and even to do inference with, which I talked about, because you have to multiply and add all these weights every single time. But there are also some other practical challenges. One challenge is that in any like real world NLP system, you probably need to update the model's knowledge over time. For example, let's say this is answering like, hey, what's the nearest pizza restaurant to me? And actually one of the pizza restaurants is closed this week. You don't want it to keep telling you about that one. So you'd actually like to update this model really often. And if it takes, 3 months to train, you can't do that. So that's a problem with actually stashing all the knowledge into the weights. And then the final problem is it's also hard to interpret what this is doing when it gives you those answers, or even to figure out how to trust those answers. Once it tells you this, how do you know whether there are like real sources backing this up, or it just kind of hallucinated that answer and actually, gastric acid has nothing to do with this? It's hard to tell unless you're an expert in this topic. Okay. So let's look at just the efficiency part. So from a systems point of view, it just seems that stashing all that knowledge into the weights and then actually running the whole model each time you get an input is very inefficient. It's basically like doing a linear scan through your knowledge. So one analogy to this is if I asked you to answer this kind of scientific question and I gave you an encyclopedia, you could use that to answer the question. And your approach was, okay, I'm going to open the encyclopedia and read every page from the first page to the last page. And only when I'm done scanning through the 10,000 pages, I'll answer your question. It's not efficient. And, it's not the way that a human would do it. So what would be a lot better than a linear scan is if we could actually use lookups somehow, right? Lookups into memory are how, basically a lot of things on large data sets can be made faster. So that's the idea of this retrieval-based NLP. As I said, there are quite a few works that try to do different parts of it, and we basically came up with some improved ways of doing it over some of the past work. So the idea here is your system's still going to get some kind of question or some kind of input for a task. And you'll still have some DNNs, but you'll also have this collection of documents that's called your corpus of documents that encode the knowledge you want the model to have. So for example, this could be every page on Wikipedia, if you trust Wikipedia, or it could be other resources you think have valid knowledge in them. And when your input comes in, the first thing your model does is, based on this input, it actually will look up some some documents in this corpus and pull out documents that it thinks might be relevant to answer this question. So there's a retriever DNN, or more generally, some kind of retriever system that does that, that tells you which documents to pull out. And then once you've got those, there's something called the reader that takes the original input and takes all the relevant context you got for it and then answers it. And one of the cool things about that is it can even give you a reference to which document it got an answer from. Like, for example, if this is an extractive DNN that tells you, okay, here's its output is a pointer to like some snippet in an existing document, then you know exactly where that came from. And you can actually show that to a user and say, look, you read about this if you want to evaluate this answer. So that's the idea. So it's, lookups plus still some deep learning stuff to actually do the language processing. And the benefits of this, if it works, if it gives you high quality results, are it's a whole lot cheaper. Like these DNNs were using, just BERT, for example, which, a few years ago, that was considered a huge model, but today it's like hundreds of times smaller than something like GPT-3. So that's great. Another cool thing is you can also update your knowledge really quickly. Maybe one of these pages was wrong, or new research got published and it's not actually gastric acid. How do you make the model return a new result? Well, all you have to do is edit your corpus, delete a document, and add a new one. You can just do it in a few milliseconds. So no need to retrain for months. And then the final thing is that it's easier to interpret because you do have links to sources, although there are still DNNs. It's hard to tell why exactly this thing decided to read this, but at least for humans using the system, it's actually, you got some benefits. So we have a nice blog post on this as well that I'll mention. There's a link in here, but I'll tell you a little bit about like how to make this work and some of the things we specifically added in this field. So with our results, and this is with my student Omar Khattab and Professor Chris Potts, we basically set state-of-the-art performance on a few hard NLP tasks at much lower compute cost than before. So we looked at 3 tasks. One of them is information retrieval, which is just the search part. Can you find documents relevant to a query? And we designed this model called BERT that can match expensive ways to do retrieval that involve calling BERT a lot of times, but they can do it hundreds of times cheaper. That's actually now being used in a bunch of commercial systems and incorporated in open source ones, like this system called Vespa. So that's that. Then we looked at things that require actually, reading and answering stuff. So first on question answering, we have a paper on a QA system based on ColBERT that actually set the state-of-the-art scores in question answering on a lot of data sets and is still ahead of stuff people have published since it came out in the first half of this year. And then another one is multihop reasoning, where you're asked to verify a claim and you actually have to look across many documents, not just one to answer it. And we also set the state-of-the-art result on that. And this actually is appearing at NeurIPS this year. So that's what we've been working on. So how did we get there? So there are kind of 2 things we worked on that I'll explain how they help the system. The first is improving retrieval. So we came up with this approach called late interaction that basically lets you, when you're looking for documents relevant to a task, it lets you do some of the kind of modeling benefits that these transformer models like BERT do, but it still remains very fast to search over your collection using this. So it's about how do we do this like complex modeling of language, like attention, for example, in a way where we can still efficiently search through documents, through billions of documents maybe, and pull out the ones that match best. So that's that. And then the second thing we worked on that helped us really improve over past results here is new ways to supervise these models, where you basically can teach a model how to search for relevant documents better for a given task. And the challenge here is usually you know the answer to the task as your training label, but you don't know what you should have searched for. No human is sitting there and labeling that. And there might be many possible ways you can search. So that's the challenge. And we figured out some ways to improve the training for that. Okay. So let me talk about the retrieval part. I think it's actually nicer and it's pretty easy to understand. So how do people do retrieval based on neural networks to begin with? So there are kind of two ways that people have tried. So one way is, so imagine you have something like BERT that's good at encoding text and embedding text in a way where similar phrases with similar meanings will be given similar embeddings. So a natural way to use it for retrieval is you basically apply BERT to your queries and you apply it to your documents, and you just take the last layer out of it as your embedding, and then you do similarity search on that. So you basically, for a query and a document, it's easy to produce just a single embedding from it, and then there are data structures that can cheaply search given a vector for the nearest neighbors in a data set. So for given a query, you can very cheaply search for the documents whose embeddings are closest to it in terms of distance. So that's a very natural way to do it. You get cheap search computation. You can just encode the documents once offline, then they're sitting there in your index. And then for each query, you just have to run BERT once on it, and then you do the search, and then you've got your results. But the downside is you've condensed all the stuff that BERT is doing is condensed into like this one vector here. And it turns out you can lose a lot of, it's hard to train this to like really represent the full nuances of the text and the query and the document. So it's hard to get the highest quality with this approach. So that's that. And then the second approach that people did, that's actually the gold standard in terms of accuracy, is all-to-all interaction. So in this, what you do is you take all your documents and you take your queries, and for each query and every document, you actually run a BERT model over both things together. Like you concatenate the query and the document, and you tell it, hey, given this query and this document, how good of a match do you think it is? That's what you train it to predict. And so the nice thing about this is BERT is really good at looking at words in context. So it can look at this word in the query, given all these things in this document, what is there some way that it could be related to these, right? So it can help deal with things like, if there are, ambiguous words in a query or whatever, the context becomes a lot clearer when you can look at the document and allow them to interact one by one to give you a score. So that's what this gives you, but it's expensive to compute on all the documents. So this is actually used in search engines like Google and Bing today. And basically what they do at a high level is they run a cheap retrieval method, maybe like this one, or maybe something even cheaper, just based on text matching, to get, say, the top 1,000 documents that seem relevant to the query. And then they run this method, they run BERT basically 1,000 times to re-rank them and to give you the the ones that they think are actually best. So that's kind of what what's out there. Okay, so how can we do better than these? We'd love to have this all-to-all interaction here to get the fine-grained modeling, but we want something that's really cheap, where we're not calling BERT thousands of times doing all this computation. So this is where our approach came in, called late interaction. And basically what we discovered is that if you take your query and document and you design the system so that you run the first n-1 layers of BERT independently on each one, and then for the last layer you allow them to interact one-to-one, you can actually keep a lot of the matching power of BERT, and you can get something that's much cheaper to run, and it's actually efficient to index. So that's basically what we do. That's why it's called late interaction. We train a model that can encode both queries and documents, but they're only allowed to interact to see each other's terms in this last layer. And this last layer is basically taking each term in the query and comparing it with every term in the document and telling you which one the embedding is most similar to. So it's like a bunch of distances and a max over them. And then you sum this up to get your final score. So that's like, very, very little interaction that these embeddings can have. But it turns out when you train this, it can come really close to matching, the accuracy of the ones that allow these to interact at every layer. And the nice thing with this is basically you can take your documents and you can do all this stuff offline just once. You can run all these layers. And it turns out you can build a data structure where you stick these into an index. You stick the term embeddings into a nearest neighbor index, and then you can do this scoring computations cheaply using index lookup. So you don't have to do a linear scan over all the documents to figure this out. So you get sort of the benefits of both approaches. And these are some performance results on how it did on retrieval. This is a data set from Microsoft that we're running on. So basically, it's showing you on the y-axis is query latency and on our hardware, and on the x-axis is this MRR score, which is a score for retrieval. It's basically how often you find. It's like mean reciprocal rank. So it's basically telling you when you find answers early on, like in your search result page, when you find the right answer early on. And you can see basically before ColBERT, there were these BERT models here that were way better than anything else in MRR, but they were also costing, like 100 times or even 1,000 times more than the previous methods. And that's because they had to run this huge DNN on the top 100 or top 1,000 documents that you retrieved, and it's just like super expensive. And with ColBERT, we were able to make these close to 100 times cheaper and more or less preserve the accuracy that they get. So this is basically these are two variants of ColBERT, but it's keeping it, you get almost the same MRR. So it's a nice kind of step forward in terms of modeling these interactions. Okay, so there's another cool thing about ColBERT is you can also see how it matched things and actually understand why it did them to some extent. And this also shows you its sort of the power of actually matching using neural embeddings of each term instead of using just word matching. So for example, this is a query in this data set. When did the Transformers cartoon series come out? And this is one of the passages in the document that you're supposed to return for that and the best hit. And what I'm going to do is highlight for every word in the query, which word had the maximum similarity that ColBERT matched it with. So for example, for when, ColBERT matches it with on because they're both about time. For transformers, of course, it matches it with the word transformers, which would have been found with exact keyword matching too. For cartoon, it actually matches it with animated because animated and cartoon, mean something similar in this context, right? Animated could mean something else in other ones. And then for come out, it matches them both with released. So it's doing, these are some of these things wouldn't have been caught with simple like keyword-based matching, but they are caught with these, these learned embeddings. And one of the key things about this is also like the meaning of come out, for example, of the words come and out are different in this sentence where, come and out are together and where there's also a when in the sentence. That means there's something about release. Like you could have, sentences with these words where they mean something super different, but the model can actually look at the context of like all the words here when it comes up with those embeddings, and same down here. Okay, so that's ColBERT. That's one of the things we built on, and it's also open source. So we actually we actually also are working on a compressed version that uses very little space to store this by basically clustering all the embeddings. You can find it on this website if you want to check it out, and we're definitely happy to talk to people who may want to use it for stuff. Let's see, someone asked, can you tell us the meaning of MRR at 10 value of 0.35? Yeah, I can try. So MRR, I have to remember, MRR at 10 is, so it's mean reciprocal rank. So basically, so what we do is for every query, we look at, there's one document, like there's one right answer it should have retrieved that a human labeled. And we give it a score of 1 if this is the first hit that the system returns. So then your score is 1. If it's the second hit, your score is a half. If it's the third hit, your score is a third. If it's the fourth hit, your score is a fourth, and so on. So that's why it's called reciprocal rank. So for every query, you can see, hey, did it, where is the right answer in the list? And if it's the first one, you get 1 point. If it's the second one, you get half a point, and so on. And at 10 means we stop at the 10th one. So if it's not in the top 10 results, you get 0. You don't get like 1 out of 11 or whatever if it's the next one. And then mean reciprocal rank is averaging this out. So one way you can get MRR of 0.35 is if for 35% of the queries, you return them as your first hit, and for everything else, you didn't return it. Then your value would be 0.35. But more realistically, what's probably happening is that for most queries, your result is in the top, 3, or I guess top 6 or something like that. And so on average, you get about a third contribution from each of them. So yeah, so you can definitely, the ideal value is 1 if you always got the right answer. But for a search engine, getting the answer in the top 2 or 3 is not too bad either. Okay. All right, so I went through this. So cool. So okay, so next thing I just want to talk about briefly is the supervision for more complicated tasks. So retrieval, it's great that you can do something cheap there, but the exciting thing is how do you use it for a bigger NLP task you have? And so one example of that is question answering. So this task is harder than retrieval. In retrieval, you put in a query, we just want to find the best hit in the, the best page on the web that people want to see. For this, you put in a question and you're supposed to get back a string. Like, for example, where does the Volga River end? It ends at the Caspian Sea. And we're looking at extractive QA, where you're supposed to take a substring of one of the documents and return that. But you could do it in other ways too. So what's the problem with this? So the problem here is if you're going to do this using retrieval, it's hard to supervise the retrieval given your training data set. The training data set has questions and answers, right? But the retriever needs to know which document you should retrieve to get that answer. So, given this question, like what pages should I pull out of Wikipedia that are likely to tell me, where the server ends? And no one told us. There might be multiple pages that contain the answer. And so how do we know like which one we're actually supposed to pull? So the retriever really needs question, positive passages, and negative passages so that it learns to distinguish, good pages to pull out from bad ones. And we don't really have that. So that's sort of the question. So basically, in a nutshell, what we did is something called relevance guided supervision, which allows you to take an initial retriever that maybe isn't great for question answering and gradually make it better specifically for the task of answering questions. Before us, a lot of systems like either use an off-the-shelf retriever and never tried to make it good for questions. So then, if it gives you back the wrong document, you just can't answer the question. They just focused on answering it if it happens to find the right one. Or people had other ways of training the retriever that were pretty expensive, basically, and didn't give you great results, at least compared to what we did. So what we do, basically, we came up with a way to guide the retriever based on just knowing the final answers. So what you need for it is you need an initial retriever that can be even a simple like text matching thing, like BM25 is a traditional text-based index, or something like ColBERT that was just trained for search can be your initial retriever. And then you also need a heuristic about, given some passages, which ones are likely to be useful for answering a question. And in our case, this was easy to come up with because we just said, hey, if the answer like Caspian Sea appears somewhere in that passage, then we're going to consider it a good passage to retrieve. And if it doesn't, then it's definitely bad. There's no way we could answer the question correctly if the thing we pulled out doesn't have the answer in it. So that's what we had. And what this does is it basically does this this loop where we train a new retriever a few times using the passages that were pulled from the old one. So what we can do is we can take the first retriever and find, for every question, find the top passages that it pulls out, whatever it's doing. So you just put in the question, pull out the top passages. So for example, for where does the Volga River end, there'll be all kinds of passages retrieved, and some of them are not even about the river. Some of them are about it, but don't contain Caspian Sea, so they're not actually good for answering our question. And then some of them are about it and do contain Caspian Sea in it. Okay, so that's what we get. And now we can apply the heuristic that we had. We can take the highest rank passages that pass it and use them as weak positives. So that would be these ones that contain Caspian Sea. And then we can get negative passages either from the whole data set, or we can even take ones that the retriever pulled out and say, look, those are bad. You should not, you shouldn't retrieve this if you get this kind of question. And now we can train using these positives and negatives. We can train a new retriever such as ColBERT that's going to pull them out. And we can actually also train the reader to take these passages and answer our question if you want. Okay. And then the final thing we can do is we can just repeat this process at the time. So we swap in our retriever with the one we just trained, and we do this again. And over time, we're going to get a retriever that aims to find pages that don't just match a lot of keywords, but actually seem like they could answer that question. Like, this is a thing about a river that might tell us something about its geography, or this is a thing about the World Cup that specifically talks about winning, or something like that, or about people, right, or something like that. So that's what we're trying to do here. And then, of course, you can keep repeating this a few times. So that's kind of how it works in a nutshell. And these are some of the results on these different QA data sets that people have. So you can see it's doing better in in these scores than the previous methods. So some of these methods like Realm and DPR and RAG are also retrieval-based methods from Google and Facebook, but they don't use the nice kind of supervision method we have, or the ColBERT representation that allows you to match things in context. So we did better than those. And then another thing that's interesting here is we also compared it with people who train large language models specifically to answer natural questions. And these have way more parameters than ColBERT-QA does, and they're not doing as well at answering these questions. So of course, I'm sure it's possible to train them even better. This was kind of trying to see, can you fine tune these or prompt them or whatever that people are excited about doing with the huge models. But the point is, we're competitive with both things that explicitly use retrieval and with these really expensive things. Okay. So that's question answering. Let me see, there's actually a question in the chat. Let's see. Oh yeah, one thing is here, yeah, it's a good question from Dave. Some retrieval systems allow you to search for a Boolean expression. Can you do that with something like ColBERT? It's a great question. I haven't really seen work on it. I think this would be an excellent thing to study. Like, if you say Volga River and, whatever, some other river, is it okay if it looks for synonyms? Like, what does that user interface even mean? I think it would be cool to do that. I think ColBERT will, well, the data sets we use, I don't think have that kind of query. So I don't know how well it would do. I don't think it could learn what the Boolean expressions mean on its own, but who knows? Yeah. Okay, cool. And then the final thing I'll talk about really briefly is multi-hop reasoning. This is the hardest problem we tried to use retrieval on. So in this, you're given a collection with some knowledge, and you're also given a claim that you're trying to verify. Is this true or false? So for example, is it true that the MVP of a game that Red Flaherty umpired was elected to the Baseball Hall of Fame? So this is actually pretty hard to answer. I mean, I don't know much about baseball. Maybe for other people, it's super easy. And if I had to answer this, I would probably fire up Google or Wikipedia or something and do multiple searches. Maybe I would first search for red flaherty and see what games did this person umpire, and there are probably hundreds of games that red umpired, but maybe there are some games in there that I think are especially relevant to Baseball Hall of Fame. So I would look, are there any like huge games? And then for each of those games, I would have to look up who's the MVP, and did that person make it into the Hall of Fame? So it's a pretty hard thing to answer. And so how can you do it? So in these data sets that are designed for these tasks, they actually base them on things you can verify in a certain number of hops using Wikipedia. So for example, one way you might find this answer using Wikipedia is if you first search for red flaherty, you would find that he umpired a number of World Series. And those are pretty big games in baseball. So pretty good bet that if like anyone, he ever worked with any big players, they might have been in those World Series, and they might have been, they might have made it to the Hall of Fame. And then, okay, these are a lot of things to look up. If you happen to look up the World Series from 1965, it turns out that its MVP is Sandy Koufax. And then if you happen to look up Sandy Koufax, it turns out he was elected to the Baseball Hall of Fame. So it's a whole kind of research project to even look through Wikipedia for all this stuff and try to figure out, is this claim true or false? And so this was a question that took 3 lookups to answer. In the data set we're looking at called Hover, there are questions that with up to 4 different hops, basically. Okay. So this is a, and so this one is true. So this is what we did. Actually, let me go to, let's see where we are here. Let me go, oops. Well, whatever. Yeah, so basically it's a pretty hard question, and we came up with a way to both supervise this and make it efficient to search, through many different kind of clues in the question and in the documents you find in parallel. So basically it's, it uses some of the same kind of tools as ColBERT-QA, but it does a few things differently. So the first thing we do, we get the query and we retrieve pages that might be similar to it. And then we actually have this new component, the condenser, that tries to summarize facts from all the pages it retrieved, and that might be relevant to the query. So basically you produce some new embeddings based on those. And then you augment the query with those. So like you add them into the query, and then you search again based on that. So this ends up allowing you to do sort of a breadth first search over the relevant knowledge, where, when you get this first one, you look like you remember that, oh, okay, red flaherty, there were a bunch of things in that article that seemed relevant to our thing, like say World Series for these different years. And then the next time you search the data set, you're searching for those terms across the documents you pulled out, and you pull out things that are somehow relevant to making progress. So it turns out if you run through this a few times, you can actually find good answers for a lot of the questions in these pretty difficult data sets that people came up with. And once you're done doing this a few times, you have again a reader that takes all this condensed knowledge and tries to answer true or false. Okay. So this is we ran this on bunch of data sets. The hardest one we ran in is called Hover, and we actually set the state of the art there, and we actually beat the previous thing by about 40 points on this. One of the nice things about it, I don't know if it's covered in these. Yeah, I guess this is a more detailed look at the results. But basically, one of the cool things about it is with our system Baleen, even with 4 hops, this F1 score, which captures how well we're retrieving the relevant documents, got close to 80%. So that means that we're actually retrieving a lot of the things that are relevant, basically, to answering the question. So, I mean, we could do a little bit better in that, and we could definitely do better once we retrieve them and actually reading them to answer the question. But we're actually doing pretty well on some of these on even finding the things, which is, pretty surprising because there's so much stuff you can search given a question like that. And overall, our verification accuracy was 84.5, and human on this is 88. So, we're not quite matching humans on this hard task, but we're definitely closer than any kind of previous thing. And we also haven't really optimized the reader part of this. So we think hopefully with more work, we can get even closer. So that's multi-hop reasoning. So that's mostly what I wanted to talk about. I hope it's given you some interesting things to consider. These are all this stuff is open source, and as I said, we'd love to talk with people who might want to use some of these. So there are a lot of ways to improve large-scale ML. There's definitely a lot on the system side, but I'm also excited about the model design itself. And in NLP specifically, this retrieval approach I think is super interesting for a number of reasons. And we're working on applying it to other tasks too. And we'd love to chat more if anyone wants to use this type of thing. So thanks. Let's see. Yeah, happy to answer questions.
Thank you very much, Matei. Guys, feel free now to ask questions directly. So Ramakrishna, feel free to ask the question you posted if you like, for everyone.
Yeah, Matei, this is Randy here. Very nice talking to you. So my question was really about the formula that you used for WT minus 1 instead of directly using WT minus 1 for WT in your gradient formula. Shouldn't you really use the correct substituted value? So effectively, instead of saying WT minus 1, it should have been WT minus the f of the next step.
Ramakrishna, sorry, it's very hard to hear you, so I guess it will be easier to actually read it from the chat.
Oh. Yeah, you did type it in, so it looks you typed in a whole bunch of LaTeX.
Yeah.
Yeah, maybe I missed something in the formula. I don't know. I thought the right one, but maybe I missed something in there. It should be. I mean, usually you take your old weight and you add something times the gradient to it, and the point. Yeah, I mean, we're adding. The point was that the gradient we added came from t minus 1. The weight we added, maybe it should also be from t minus 1, but I think we have the weight at t as well. But maybe I missed something there. I'd have to look it up in the. Yeah.
It's not super important. It's just a technical thing.
Yeah, we do have it written up in a paper too. So maybe if I missed a t, that should have been a t minus 1. Hopefully, it can be fixed there. Yeah.
Matei, I have a question actually. I think it's very exciting, really. Not just from the engineering standpoint, but from explainability standpoint, and also I think it has implication in removing bias. So maybe you can, I don't know if you guys thought already, right? But like from what I gather from your architecture, so first of all, separate language processing from knowledge. So knowledge is a document database. And so it's easy now to update knowledge, right? Secondly, you avoid, you omit the final layer. And so when you do the matching, right? And so basically you can kind of compose it later. And so when you interpret the results, right, you can focus on individual components of the query, and then you can see what produced, right, what produced the match. So I think, correct me if I'm wrong, but it really makes it easier to remove bias, because let's say you flag the biased expression. Now you can say what led, first of all, to the match in the query to the biased answer. Secondly, you can trace the biased answer to the knowledge base.
Yep.
And you can update the knowledge base.
Yeah, you can fix it.
Are you guys doing anything in this direction?
Yeah, we haven't done too much with this yet, but it makes a lot of sense. And yeah, we'd love to do more in this area. I think, one of the like interesting challenges here is, I did say we want to separate the knowledge and from that model, the retriever model should just do language processing. But actually one question is, hey, how often does that happen? Like, does it actually, maybe the model memorizes some facts, which would be bad, right? If that basic DNN, like if it thinks it knows the answer and it doesn't even look it up, right? It's like the know-it-all friend who says, oh, I know there's, and they don't actually look it up in Wikipedia. So that there's an interesting question of, does it do that? And also maybe we can train it not to do that. Like one thing we're exploring is, what if when we train it, while training, we actually like edit some of the passages. Like we say, whatever the, Volga River doesn't end at the Caspian Sea or whatever. And like we train it to be robust to that. Basically, maybe you can teach a model that like really looks up knowledge as opposed to trying to memorize stuff or be biased. So yeah, that's an interesting thing. The other thing is as part of that, like you could imagine that the model, if you train it on some biased corpus, it will still learn bias. It will still make embeddings close to each other that shouldn't be. But maybe there are some other techniques you can use to prevent that. The nice thing is at least you trace where everything came from, and you can fix it you can see, okay, if this source is like really wrong, let's fix it. And maybe even if some phrases are matching that shouldn't match, you can actually tell it not to do that. So that's kind of nice.
Right. It's really struck me like this is true MLC spirit, because you bring notions such as modularity, right? Decoupling of knowledge base and the lookup mechanism, right? And then you also have the iteration when you look for the retrievers, right? And you refine retrievers through iteration. So I think, we need to teach the large models to be ethical and good. And so you kind of create several points where we can insert the teaching, right? Because we can see like, how do you do iterative retrievers? Maybe you should filter the way you get the retrievers also, right? Debiasing the retrievers.
Yeah, that's true.
themselves.
You could do that. Yeah. I think it's a very open field, and it gives you, even the fact that it's so much faster to run stuff lets you experiment with stuff a lot faster. So yeah, we'd love to try stuff like that.
Awesome.
Yeah.
Any other questions, guys? Feel free to ask. Can I ask, what's the implementation? How did you guys implement this?
Yeah, I think, the current system, so I think we coded up most of the stuff in PyTorch, and we have, for the indexing, we used face, nearest neighbor index on Facebook, but actually in the last version, I talked about this compressed ColBERT. We actually we don't even need to index a lot of vectors. We first cluster them, and then we just index the cluster center. So we're not really bottlenecked on the nearest neighbor thing very much. So yeah, and we actually built this whole thing. If you look at our code base, it's actually like this isn't a standard thing you can easily train in PyTorch. So we actually have a whole kind of code base with concepts like indexers and rankers and stuff where you can train these, and where you can sort of pause and checkpoint your job and start it again. So we're trying to build up some infrastructure around this, because at the beginning we just had a whole bunch of like scripts, and it was enough to write a paper, but it got super messy, super hard to modify. So now we've been spending some time factoring them into nice abstractions. I think we'll probably post some kind of blog post about that soon, as we're refining this. We're still working on a few loose ends there, but it'll be like at the end of the day, that retrieval guided supervision thing I talked about will be like 5 or 6 lines of code with our high level API, like build index 1, search, build index 2. That's the hope. So yeah.
Got it. There is another question from Dave. Dave, feel free to ask.
I can also read it if you prefer, but
yeah, sure.
Yeah. So the question is, could you explain more about how neural document retrieval could be used for technical documents like for archive? I think people have used this kind of approach in pretty technical settings, and it can be made to work pretty well. You need to, you do want to train or fine tune on data from that domain. So some examples, we've been using it for stack exchange questions in different fields. One of the things we've been working on is, it's a lot of work to train something like ColBERT and to find a huge data set. So we want to basically train one once and then make it easy for you to fine tune for your domain. And we're using stack exchange for that. Like take the top, take stack exchange questions on, Java programming and see how we can tune ColBERT to be good at that. Some terms in there will gain different meanings than they do in like general English, or take stack exchange questions on, linear algebra or whatever. So you can find lots of specialized domains. And, we've been able to do like reasonably well by fine tuning using a small amount of data. We like stack exchange because it's got a question and answers and even a long form question. So it has some structure that you can use to teach stuff. So like, for example, if we separate all the answers from the questions, we can see, can we learn to like match each question with its answer or something? And separately from that, there's also one company we've been working with that's basically like a tech platform, like an enterprise, tech company that has, its documentation, and it's very technical, lots of terms specific to them. And they want to build a NLP-based system for searching that. And they've been getting pretty good results. They trained their own, like they fine-tuned models for their documentation. But they have very few like actual labeled examples. And, they're trying to adapt something like ColBERT to work with their domain. So it's doing better than whatever, like search system they were using before. I also see a question from Amir. I don't know if you want to ask, I can read it.
Yes, so you said the compressed ColBERT uses clustered centroids, which is, I believe, like what the inverted list file or inverted file product quantized face does. Is that similar?
Oh yeah, it may be. Yeah, it may be similar to that. Yes. I think it's similar to that approach then. Yeah, we did. I mean, we did some, like in these things, you can often do a little bit of fine tuning and stuff after too. So we did do that. We didn't just like make a list, but we can basically fine tune the ColBERT model. Like once we compress everything, we can fine tune it a bit so it deals better with, the compressed things. But yeah, it's definitely a similar approach. Yeah.
Any other questions, guys? If not, maybe I'll ask another question because it's a really interesting area. So basically, you presented several really cool use cases, right? So you do question answering and you do multi-hop reasoning. And obviously, a lot of these things you can do in a lab in some kind of abstract fashion. You can think, what are the kind of questions, right? Where does the old Volga River go and stuff like this? But, I think the real usefulness of this area would be tested in the field. And I didn't really see like application of large language models have been mostly toy examples of disposable copy, like marketing copy, low importance and low risk, right? But let's say, do we want to ask a healthcare question, right? Here is a patient, right? So for instance, I just learned recently that in Moscow, they actually deployed BERT because it's very centralized. They deployed BERT and just state network of computers. So 70% of diagnoses are now made by doctors selecting something based on, based on symptoms. And I don't even know how reliable it is, but they just, they just roll it out apparently, and it's very easy, right? So, and we don't really know, right, how well it works and stuff like this. So have you guys tried to take one of these systems and deploy it in some scenario where the question and answers would matter and see what people actually do?
Yeah, that's a great question. I think the closest so far has been this one I mentioned. As this company, like large kind of enterprise tech company that's actually, like been testing this on their real searches for their like customer support system. So yeah, we're trying to find other groups as well to work with. There are some groups in the medical school here that are doing some retrieval-based stuff where we'll try it out. Yeah, but it can be hard to get access to these kinds of things. So, we're mostly yeah, we're trying to find people who already do something like this and tell them you can do it better.
So
maybe.
probably would make sense to like, because I'm thinking, right, like the evaluation of this probably belongs in CRFM, right? And we need to have probably a benchmark, right? Basically, here's a real use question answers from, sanitized from healthcare, given the set of symptoms,
that's true.
Give me the diagnosis, and maybe the next step would be to, because I think you guys really did a good job in machine learning benchmarks at Dawn Lab, and maybe this is another example where we need
that's a great idea,
approach,
like
right?
a benchmark for, language tests that actually matter. Yeah. The tricky thing with doing this with a academic benchmark, though, is people will find ways to overfit to it and to over specialize. So it's good. It's better than like Stack Exchange for sure. But it's still not as good as saying someone else was able to use it and actually got something to work. So it's a bit tricky. But of course, the benchmarks help the community compare techniques and stuff. So yeah, I think it is a good idea. Yeah.
Right, and maybe MLPerf can be one of the places where this can sit, right?
That makes a lot of sense. Yeah.
Cool. Any other questions, guys? Well, if not, it's been a very good talk and very good evening with Matei. Thank you so much, Matei. Really appreciate it, and looking forward to more great talks coming forward, guys. Submit the talk, and we'll host it.
Cool. Yeah. Thanks a lot. It's fun.
Thanks, guys.
Being here.
See you.
all.
Bye.
Mhm.